Okay, lecture 3-4, Bayes' theorem. Given two events, A and B, Bayes' theorem, also known as Bayes' rule, states that the probability of A given that B is equal to the probability of B given that A times the ratio of the probabilities of A and B. Sometimes this is written as the probability of B given that A times the probability of A divided by the probability of B given that A times probability of A plus probability of B given that not A times the probability of not A. So this is just an expansion of the probability of B in terms of conditional expressions relative to A, right? And then this last one, I've rewritten this so that the probability of A shows up just once and the probability of B given that A just shows up once. So simpler in a sense, but take it for what it's worth. Okay. This is a useful theorem for determining a test's effectiveness. If a test is performed to determine whether an event has occurred, we might ask questions like, if the test indicates that the event has occurred, what is the probability it has actually occurred? Bayes' theorem can help compute an answer. Okay, this is used a lot in things like determining how effective a test for a bad part needs to be, as an example. It's also used a lot in like medical diagnostics. For interpreting the results of a medical diagnosis, this is very useful. So it's also a little unintuitive too, so it's good to use. People argued about this for a long time. There's a fun problem I recommend you look up called the Monty problem. It's very fascinating. So, testing outcomes. The test can be either positive or negative, meaning it can either indicate or not indicate that A has occurred. Furthermore, this result can be either true or false. So the test could be a positive test, but it might actually not have occurred. So that would be a negative, that would be a false positive. Or the test could indicate that the event did not occur and it actually did occur, in which case it would be a false negative. So there are four options then. Consider an event A and an event that is a test result B, indicating that event A has occurred. Table 3.1 shows these four possible test outcomes. Event A occurring can lead to a true positive or a false negative, whereas not A can lead to a true negative or a false positive. So, say there's like the easiest example to like bring it home to us is like the test for something. Let's say it's a pregnancy test, okay? So you might be that you are pregnant. The test might say you are pregnant. It might also say you're not pregnant, in which case it would be false positive. You might not be pregnant. The pregnancy test might say that you are pregnant. The test says you're not and you're not, so that's true. If the test says that you are pregnant when you are not pregnant, that's a false positive. And when you are pregnant and it says that you're not pregnant, that is a false negative. Okay. Terminology is important here. Probability of a true positive is the probability of the test coming out positive given that the situation actually occurred. So this is the probability of a positive pregnancy test given that you are in fact pregnant. This is called sensitivity or detection rate. Okay? The probability of a true negative is the probability of getting a negative test result, not B, given that not A. Given that, say in this case of the example, that you're not pregnant, it'll say you're not pregnant. False positive is that the probability that you're going to get a positive result when you're actually not pregnant, and then false negative is the probability that you're going to get a negative result given that you are pregnant. Okay, so those are some terms that are important. Clearly, the desirable result for any test is that it is true. So you'll want to be right here, right? This is good. This is bad. You don't want to have the test giving you false positives or negatives. However, no test is true 100% of the time. So sometimes it is desirable to err on the side of the false positive, as in the case of a medical diagnostic. Say, I mean, it's not awesome, but if you find out that you are like diagnosed with cancer and then you find out later you don't have cancer, that's a good way to go about things. I mean, it's better than the opposite where they missed it and then later you find out that you had it. Okay, so medical diagnostics, I mean, it's not great to have a false positive, but it's also not as important as avoiding the false negative. False negatives very important, are very bad in medical diagnostics. Other times, it's more desirable to err on the side of a false negative, as in the case of testing for defects in manufactured balloons, when a false negative isn't a big deal, right? That one balloon goes out, it's got a hole in it. Probably not that big of a deal. You also don't want to be constantly stopping production because you have a defective balloon, but it turns out to be that it's not defective and you just stopped things for no reason. Yeah. I mean, it just depends on the situation, right? Sometimes you got to err on one side, sometimes on the other side. Posterior probabilities. Oh, shoot. I don't know if my mic was working during that. We'll see. Anyways. Returning to Bayes' theorem, we can evaluate the posterior probability of A given that B, of the event A having occurred given that the test B is positive. We can do that given information that includes the prior probability, which is the probability of A, of the event A occurring. The form in equation 3.3 or 3.4 is typically useful because it uses commonly known test probabilities of the true positive, probability of B given that A, and of the false positive, probability of B given that not A. We calculate the probability of A given that B when we want to interpret test results. So this is like, okay, I got a test that says I have a certain disease and I want to go back and say, okay, this test has some probability of detecting this situation if I have this. Also, there's some probability that I have this that is maybe very small. Like the probability of having some rare disease is actually very small, which is part of why diagnosing it is very hard, because the prior probability is so low. You have to have a very, very accurate test, a very, very sensitive test to detect it. So, some interesting results can be found from this. For instance, if we let the probability of B given that A equal the probability of not B given that not A, which is saying that the sensitivity equals the specificity, which is not always true. It's sometimes we're better at detecting when the thing occurs than when it doesn't occur. Sometimes, it's asymmetrical. But this does happen, reasonably frequently, that we can say this is a useful thing to develop. And realize that the probability of B given that not A plus the probability of not B given that not A equals 1. So when the actual event is not A, we have to either have the test come out positive or negative, right? So those probabilities have to add up to 1. We can derive the expression probability of B given that not A is equal to 1 minus the probability of B given that A. Okay, so that I used this expression and this expression to come up with that. Using this and the fact that the probability of not A is equal to 1 minus the probability of A, because either A or not A, we're assuming, either has to occur or not occur. In equation 3-4 gives, recall we've assumed sensitivity equals specificity. So this equation only applies when that is true, right? We can simplify down to here or down to here, which is to say we have the probability of A given that B. So probability of the event having occurred given that the test says it has occurred. In terms of the probability of the sensitivity, so the probability of a true positive, and the probability of A occurring. So we plot this in figure 3.1. So on the horizontal axis here, I've chosen to put probability of A. A lot of times the thing that you're trying to detect isn't very common, right? It's relatively rare. So given that you're testing something, maybe there's only a very small chance that it is actually happening. So I did from 0 to 1% probability that this event A occurs. Okay, if that's the case, if it's that low, then I gave a curve for this, which is the probability of the event occurring. This is the posterior probability, the probability of the event having occurred given that the test has says that it did occur. So we want this to be close to 1, right? We want this to be high. We want the probability of this thing having happened, given that the test result says that it's happened, to be high. And of course it is high when I said that the sensitivity was 1. So the probability of B given that A, if we have a perfectly sensitive test that detects every single one of these situations, every single one of these events occurring, we can be confident that if the test says it, it actually happened. Okay? However, you don't have to go down very far. This is 4 nines, okay? So 99.99 being our probability of the event having occurred, given that we've indicated that it occurred, which is a pretty darn good test, right? Even if you have a 1% chance of that thing happening at all, then you're still only at 90% if that test result comes back positive. Okay? The test result comes back positive, and the probability of having the thing was 1 in, say, 100. 1 in 1,000. Then you're down at around 50%. Okay? And if that probability of that thing happening was like 1 in 10,000, then you're down, it's like a very, very low probability that you actually have the diagnosis or that the event actually occurred. Even though we have 99.99% sensitivity. The rareness of the event affects the ability for you to infer that the event occurred. And that's the probability of A that shows up in there. If the probability of A is small, it really throws off everything else. So then if you say, okay, 99.9% chance, I mean, even if there's only a 1% chance, even if there's 1% chance of something happening, if the test indicates that it is the case, then still it's only 50% chance if the result came back positive that thing actually happened. So 99.9 is not very good for something that's rare. 99% sounds decent, but in fact is, 90% is the slowest curve, I guess. I seem to have one more curve than I have legend values. I'll have to figure out why that is. But I think that it's clear that the probability of the event occurring at all being low really affects how much you can trust the test, even if it's a really good test. And the test has to be very, very, very good if you're going to detect something that's very, very rare. They're essentially fighting each other, those two. Okay? Dang, this would have been nicer if I had 5 traces on instead of 4. I feel like something happened there. Anyways, I'll fix it. Okay, so let's look at this example. Bayes' theorem. Suppose 0.1% of springs manufactured at a given plant are defective. Suppose you need to design a test that has sensitivity and specificity 99%. What probability should your test have, given that a part is defective, of indicating that it is actually so? Well, wait. I rewrote this at the last minute last night at 1 a.m. or something, and then I screwed it up. So let's take this out, because that last part was what sensitivity should you have. So suppose you need to design a test that has the posterior probability of or no, let's see, what did I want you guys to calculate? I wanted you guys to calculate the sensitivity and specificity required. So what this is the probability of A given that B, the posterior probability. It has posterior probability of A given that B, and 99%. What probability should test add given that a part is defective of indicating that it's actually so? And I want to say assume sensitivity, which is what I just said here. So what sensitivity do you need? Assume sensitivity and specificity can be made equal. Okay. It's funny when you go back and try to improve something and you make it worse. So, this did not show up. I'll switch over to the I have somewhere here. Wow. I don't seem to have it. My Jupyter notebook. There it is. I found it. We're back in business. This is actually how I did it, and I thought that this was showing up in the notes, but it did not show up, so we'll just go to this instead. Yeah, I linked the notebook. I published the notebook into LaTeX, and it gets included in my, yeah. In the version of this PDF, I can see it looks great, but I thought that you guys could see it too, but you can't. So, great. So, I'm going to use SymPy to do this. So first I define my symbolic variables, and then beginning with Bayes' theorem, and assuming the sensitivity and specificity are equal, we can derive the following expression for the posterior probability of A given that B. I start out with the original form of the equation, okay, which is probability of A given that B equals probability of B given that A times probability of A divided by the probability of B. So start out with that first form, which is the form given way up here, yeah. And then I say, okay, probability of B is, using the conditional probability idea, it's the probability of B given that A times probability of A plus the probability of B given that not A times the probability of not A. Okay, so there's that substitution I'll make. I'll also make the substitution that probability of B given that not A is 1 minus probability of B given that A, which is the result that I found when I assumed that the sensitivity and specificity are the same. Right? This is equation 3.5. So I just used that equation, that result. And then I said, okay, if the probability of not A and the probability of A have to equal 1, then you can say the probability of not A is just 1 minus the probability of A. And then I solve that, or I just substitute them in, and this is the expression that I have left. So I'm going to solve this for probability of B given that A, the quantity we seek. So this is what probability of B given that A shows up 3 places. This is why I started using symbolic toolbox, because I was not really liking how that was going on paper. Solve for probability of B given that A, which shows up 3 places in this ratio. And so I just used the symbolic solver and display it here, and it isn't too bad, but it was more than I wanted to do by hand. And then I substitute in the probability, which is the probability of A being 0.1%, right? And the probability of A given that B, which is the one that we want, right? We want, if a test result comes back positive, if we think we've correctly identified a defective part, I want there to be a 99% chance that that part is actually defective. Okay, I don't, maybe it is a thing where I'm making like cheap springs and I don't want that production line to stop unless I'm really sure that this part is defective. And so I want there to be a 99% chance if we think we've detected a defect that it's actually defective. So if I want to find out what the probability is that I need for my sensitivity, I need 0.9998988 whatever percent probability, which is rather high. So a very tall order, right? I really need a very high sensitivity if this is going to be the case, if I'm going to get to this level. Okay, so yeah, so you're even though, I mean, 0.1% is, not even a super low defective rate. I mean, depending on your manufacturing thing, you could have much lower than that. You have to have a very, very sensitive test in order to get this posterior probability that you want. Okay. So that's the idea. That's kind of the idea with these things. Did you guys have questions about this?
So confusing.
Yeah.
What you say? For a given time, there is 0.1% chance that the part that the spring is defective.
Yeah.
Defective.
Uh-huh.
And then design a test that has. What do you mean design a test?
So say you're in a manufacturing environment, and they say, okay, we're putting out these defective parts sometimes, and we need to detect when that happens, right? We want to have a test that determines, like, okay, this part is defective, and what we're worried about is that if one's defective and you stop the line, we're going to be losing money when it's stopped. So we want this thing, if you're going to stop the line, we want this thing to only give, to stop the line when it's really sure that it's defective. So this test might be maybe a test of the weight of the part, or this could be some measurement of a dimension that it's doing, or it could be, there's all kinds of things. I once designed a groove detector. This part was supposed to have a groove cut into it, and so I would have, as these things would go by, if it had the groove, it would just slide on past, but if it didn't have the groove, it would depress this little button, and there would be a sensor that got tripped, and then it would stop the manufacturer, because this was one of those ones where it was very bad to put through a bad part. So it would stop the machine, and then a machinist would have to go over and figure out what's going on. And so this requirement is actually a pretty difficult one to have. So you have to be, if you're going to be 99% sure that if the test is positive that the thing's actually defective, that's asking you to be very, very sensitive, and it might be asking too much. So you could say, okay, you could find out what your sensitivity is, and knowing what your sensitivity is before you've created your little, sensor or whatever, is hard to know, but you then would test it, right? You'd say, okay, I'm going to put through bad parts and see how frequently it catches the bad parts. And when it is bad, actually bad, then I'll get like a point, and if it thinks it detects one that's not actually bad, then it's going to have, it's going to affect the statistic the other way. So what you're going to want is to end up with one that's 99% of the time, when it says it's defective, it's actually defective. So that's the design goal. I'll update this too. I should have. This was worded poorly when I went back and tried to make it a little bit easier to read, and it made it harder to read because it was wrong. So
probability of A is the probability that your spring is defective.
yeah.
And then probability that A given B is the probability of a true test.
Probability of A given that B is probability of the spring being defective if your test is saying that it is.
Okay. And then probability of B given A would be
The probability that given that a spring is defective, that the test indicates that it's defective.
Okay, so that's what we're going for then.
Yeah.
Okay.
So we're going for a really high probability of B given that A. So really high probability of catching a defective part. Really high sensitivity. And so when you're testing this thing, if you have to get to that high of a probability, you're going to have to do a lot of tests, right? I mean, you're going to know pretty quickly if you're even in the ballpark, because if you even have one mistake early on, you're not in good shape, right? But you have to take thousands of data points for it just to even have any sense of whether or not this is happening. When we get to statistics, we'll have an idea. We'll talk more about error bars and how confident you can be in your estimate, too. Okay. It's not all card games here, dice rolling. Also springs.
It seems more practical than the dice because you are not in casino.
Yeah. That's right. That's right. Well, I mean, you got to do something with all this engineering job money you're going to get. So you got to go out there and spend it at the casino.
So you have to learn probability too.
All right. See you guys next time.